All right, so now we're actually recording. So we already said reaction rates are how fast or slow a reaction can go. And if you adjust the molarity of the solution, you can make things move faster. Molarity is concentration, how close the particles are together, moles per liter. We're going to get into those things really closely. We also talked about you could speed up the decomposition of something by heating it. You could slow down the decomposition of something by cooling it. We're going to hit a lot of those things over and over and over again. And we just watched the iodine clock video. For those of you at home, feel free to watch that in your free time. It's amazing. We're also going to talk about something called chemical equilibrium today. Here is a reaction that most of you have achieved at home at some point. It's a very exciting reaction. It's called boiling. Right? Can you reverse the boiling reaction process? Can you condense it? Heck yes. And that's a great example of an equilibrium reaction. Here I have a bottle of water in my hand, definitely not taking it from a student's desk. And you can hear the crinkliness of the bottle. Thank you, sir, for supplying this bottle. Trapped inside this water bottle, as you can imagine on the other side of the line, is water. And then above the water is some gas, and there's actually some steam, water vapor in that gas area. Some of the gas becomes liquid, some of the liquid becomes water, and it keeps going back and forth. That's why there's two arrows here. And sometimes instead of two arrows, you will see a two-headed arrow like that, or if they're super lazy, they'll make the arrows look like that, like they couldn't find the other half of the arrowhead when they put it on. All of those mean that the reaction is reversible. It can go forward and backward. Specifically with this reaction, how do you make it go forward at home? Heat. You heat it up and it goes this way. Cool it down and it comes back again, right? And you can make it bounce back and forth. You have this energy diagram. Weird noises coming through the wall. Energy diagram, and this kind of looks like the energy diagram in your notes, slightly different. These actually look a little bit better. But we've seen this in the past. We did energy. Here's the reactants. They have a certain amount of energy. Here's the products. They have less. Would this be exo or endothermic? Exo. Very good, Mrs. Andres. It would be exothermic because if you compare the beginning to the end, you are losing energy. This reaction is exothermic, and it is releasing energy. Why is that blinking? Because it's because we're talking to you. Okay. Activation energy. I'm sorry. The other one, we started with reactants. We end up higher at the end. That is endothermic. And that's when it's being absorbed. Which one of these graphs represents boiling water? The endo, right? Yeah, the endo. You have water, you put energy in, it boils and makes steam. You okay? All right. And versus the exo, this might be condensation, except this is weird for condensation. You don't usually have to put energy in to then get it to condense, do you? That's not a good condensation graph. A condensation graph would just look like this, which would be like a straight drop. This first graph might be like an explosion, like we're heating up the bomb for some reason, and BAM! And then it's exploded and released all of the energy. That's not a good idea. Collisions and more collisions. In order for a reaction to occur, the chemicals have to collide. Over here, I actually have some hydrogen and some oxygen that I produced earlier in the day. Let's see if I can get this to work. Can you guys see that? Yeah. Fantastic. Someone turn the lights on over here. You people in this room with me right now. So, oh, that's not making anyone sick or anything. It's like sideways. Oh. Oh, that was a great noise. Shall we spin? Yeah. That's less sideways. I'm going to zoom out. Can't zoom out? Oh, I don't want to zoom in. It's going great. So earlier in the day, I actually produced some hydrogen and oxygen in this thing that has a very fun name, and I think this class is going to... This is called a Hoffman apparatus. For real. This thing's called a Hoffman apparatus. It has these two metal electrodes, wires attached, and then this battery. And when you connect the battery to the Hoffman apparatus, it will electrolyze water. And you see those bubbles? Yeah, those bubbles are hydrogen and oxygen being produced. Each side is actually reacting, producing hydrogen and oxygen. Hydrogen is incredibly flammable, especially in the presence of pure oxygen. You got me? Now, right now, they are bubbling up separate in these two things, and they're going to fill it. I am not worried about them exploding much. But that's because, can they collide? No. They are in two separate containers, so they can't collide. If they can't collide, they can't react. Just like if you don't ever meet your future wife, you can't marry her. Right? In fact, I think later we'll watch a whole video on how to get a date. It might be helpful for you. Not talking about anyone particular there. The other thing you have to have enough energy, something I'm not generally lacking in. But if you don't have enough activation energy, those molecules can hit and not have a collision. You want a really hard collision to make the explosion. With a lot of real explosions, we typically add a spark, right? Throw a little spark in there. That breaks the first molecule apart, which then releases energy, which releases the next, which releases the next. And if you ever watch any slow motion videos of explosions, you can see the concussion wave as the energy spreads out, and it's awesome. Or you can watch like fake movies where they, pretend that it's occurring, but it's still awesome. Lastly, when things react, they have to have the right orientation. And orientation is just all about how the molecules are lined up. So let's look at some molecules. And here we have some molecules. Yes, that I had a cut on my hand, sorry. These molecules are not lined up right now. Oh, look, that spun around. They will actually get attracted to each other and repelled by each other. But what if you try to bring the two white sides? Let's go, Kayla. If I try to put the two white sides up to each other, are they going to be attracted? No, why not? Yeah, they're the same pole. They're both on the same pole. They're both negative. They would kind of, when they get close to each other, they repel each other, and I like the fact that this molecule is playing along with me. That makes me so happy right now. And so, even though they're about to collide, they have to be attracted to each other also, don't they? So if I, though, just kind of hit them, they slide and twist around. And with polar molecules, that's why polar molecules are more successful, because they are attracted. Well, that's weird. We're getting a weird reverb action. Oh, my head is, that was weird. And recorded for future classes. So with polar molecules, the collisions can oftentimes be a little more successful because they are attracted to each other. These two videos are really boring. They're not nearly as good as watching this, which really just tells you how bad those videos are. All right, let's move on. So there are 4 things we can control when we're talking about reaction rates or reaction speeds. We can control the molarity. And molarity is actually 2 things. It's the moles and it's the volume. True or false, Grant Mish? I'm guessing that was true. Sounded like so molarity is moles per liter. It's a ratio of the 2 things. This is to say you could add more into the reaction, or you could change how the reaction is spread out, what volume it occupies. I briefly toyed with having this lecture all in one room and jamming all of you together. It would be a sweaty mess after a while, though. But that would be changing the moles, right? The number of people. in the space. Or volume, we've just spread you out over a larger volume and using technology to get around the problems. Temperature. Temperature is a common thing to change. How hot substances are, that's how fast they're moving. And we can control that by putting them in a freezer and boiling water, whatever. Surface area. This one is how... That's in the hallway, isn't it? Okay. How spread out. I thought it was the other room was screaming. I was really worried that something had gone wrong. Surface area is how spread out they are. Quite often we have rocks and minerals, and we want to react with them. The stuff on the inside of the rock isn't exposed, is it? So we break it apart, sledgehammer, mortar and pestle, spread it out, and then it can react faster. Lastly, we have a catalyst. A catalyst makes things happen by binding to it. In most bio classes, there's like a picture. This is my artistic talent here. Enjoy that. So this chemical fits into there. Kind of looks like Thor's hammer. Yes, listen to that guy. What you missed in the other room is somebody goes lock and key. That was good. And so when these pieces lock into this catalyst, the catalyst then slams them together, and they make one new thing, which I'm going to try to draw combined, and it's going to look hideous. Yeah, I can hear you over there mocking my ability to draw. Hey, look, it's combined together. That's beautiful. And biology textbooks tend to represent the catalyst with some sort of simplistic shape. They do that because the actual molecule can be 200 or 300 atoms in size. Like, think DNA, but smaller. And it will grab onto these molecules, and when it grabs onto them, it twists the shape around and then smashes them together. All right, now to address some of your dating issues. So I like that video because it does kind of represent things coming together. I do have one issue with it, though. If we actually were constantly colliding, I think more than just dating would occur. There'd also be fights. So I think we'd have an increase of a couple different things. But so let's just kind of go through these analogies. As they shrink the hull size, people are closer together. That's the same as if you have, in a car engine, you have pistons that go up and down, and they contain the gasoline and the oxygen. And the piston goes down, compresses the gasoline and the oxygen together, and then bam! The spark plug ignites them while they're close together. So they increase the concentration, increasing the likelihood they'll explode and react. Increase the number of particles. I think we've already got a problem with school population. We're already at like 250, 300 people more than we're supposed to have. But we're doing okay. Some of you guys don't look too impacted by it. That's the same as increasing the number of particles, putting more gasoline into the piston. That doesn't necessarily work, though. Heating them up, making them move faster. They're talking about time there. That's not quite true, but speeding the particles up, I really feel like this would be like giving all of the students like straight Pez'd, dry, or what's that unicorn frappuccino thingy? Just straight sugar and making you hyperactive and move. Might have a couple drawbacks. Breaking the students apart as they move, that's the same as grinding the solids up and spreading them up. Hiring a matchmaker, no one does that anymore. It's 2017. People are on, what are you on? Tinder? You're on Tinder? Okay. Yeah, this guy's on Tinder over here. Or using a catalyst. A catalyst brings the pieces together so they can react. All right, let's get back to the notes. So, concentration, temperature, surface area, catalyst. Let's take a second. Actually, we need to add a line to this graph in your notes. Let's add line E. And then let's add a question which represents the lollipop guild. No, which represents the reactant energy. This is my very best Promethean board handwriting. Okay, so I'm going to call on a couple people in this room. You with the Redskin shirt on. Which of these shows how the energy is changing from the beginning to the end? Is it B, C, D, A, or E? Which one represents how the energy is changing from the beginning to the end? B. Yes, it is B. Yeah, B represents the beginning to end. Starts here and then it drops to there. Is this reaction endo or exothermic? Other room. Yeah, it is exothermic. The activation energy is this peak here. It is D for delta. Energy of the products, what do you think? Other room, you could talk too. What's the energy of the products? A? That's what I think I heard. Yes, A. It's kind of cutting out. This is a slower energy pathway. That's our catalyst. And that means the energy of the reactants must be E. Alrighty. We had to add a question because not quite everything was labeled on there. Let's just go ahead and blame that on Mr. Shangri where it belongs. All right. The equilibrium condition. So here we have a reaction that is reversible, kind of like your boiling condensation. By changing the energy, the temperature, you can actually force a reaction to go in two directions and reverse it. And over here, I have, yeah, I do. Let's see. Oh, that's still in the hot water. I have a couple test tubes. Miss Andres, I'm going to need some ice again. I have a couple of test tubes over here. There we go. These test tubes are, can person beside the light switch flip on a light switch for us over there? That's fine. He's currently walking over to the light switch, turning it on. Is it kind of weird how there's a delay? Yeah. So we have a couple test tubes that actually all contain the same solution. Let's see. Everything's backwards from my perspective. Are they the same color? No, they're not. The blue one was actually in hot water. Then they're in the wrong order also. Actually, they already kind of changed in color, so I might just... Thank you, hon. I called you. I just called her hon. There we go. The blue one was in hot water. The purple one is in the middle, and then the other one is pink. They're not quite extreme enough, so we're going to warm this up, warm that up, get them going here. So you can see, oh, that's, why isn't that falling out? It's upside down. All right, we'll come back to that in a minute. It's got to take a couple minutes to actually shift. While that is shifting, because the temperature of the solutions is changing, let's talk about what's going on in here. So we have a reaction with N2O4, and there's plenty of N2O4 in there to start with, but there is no NO2 to start with. And then when the reaction goes, this decreases and levels out. This increases and levels out. But eventually they both level out. The reason I changed my voice there is this was a steeper increase than that was. It was like decreases, increases. Not just because I'm stupid. That's for... And over here, these are both pretty much level. I made them squiggly because it's not actually perfectly flat. There'd be some vibration to them. And now that they're not changing, we have achieved what's called equilibrium. And equilibrium doesn't mean you've run out of anything, because we actually still have both the reactant and the product in place. But chemists love this idea of equilibrium so much that they decided to measure it mathematically. And this is where you pull out your calculators and we do a little bit of math. All right?
You guys have calculators?
If they don't, they're in the back of the room. That's a good, I hear you. So, that used to be a calculator. Now it's a paperweight. Whoa! Why don't you give that guy a hand? He's falling out of his desk. There we go. So first things first, here we have a boring basic reaction written. I know that these are not actually elements. A and B are on the reactants side. C and D are on the product side, yes. And at equilibrium, the products and the reactants stop changing how many there are. And chemists decided to write the amounts as a ratio. And since it's not changing, they call that ratio a constant. What symbol, what letter would you pick for constant? You would probably pick C, but Einstein took that one and turned it into speed of light. Oh, the specific heat capacity is also C, isn't it? Yeah, look at that guy. I don't know his name, but he's pretty smart. And so we have stolen K for constant, so we spell constant K-O-N-S-T-A-N-T? Yeah, I think so. A-N-T? Thanks, honey. I spell so good. Me English well. So what we're going to do is we're going to write math expressions that always have the products on top and the reactants on the bottom. What goes on top? How often?
Always.
Just always. Just always, okay? That's how often they go on top and how often the others go on bottom. And so let's go back up here. You can see these reactants are on the bottom and the products are on the top. I'm about to yell, prepare yourself, if your name is Ryan in the other room. This is A plus B, but over here it's A times B. It is not A plus B in the equation. It's C times D. We're actually multiplying those values together. I only become obnoxiously loud about that because that's the most common mistake. You got me? I can't tell you how many kids, even though I give like that insane emphasis on that, they still mess it up. So whatever the value of C is and whatever the value for D is, they get multiplied together. Whatever the value for A and B are, they get multiplied together in this equation. Lastly, quite often we balance equations. There's like coefficients in front, like, hey, that's a 5, that's a 2, that's a 1, that's a, can't be a 0, 3. Those coefficients become exponents, so D would be to the 5th power, and B would be to the 2nd power. Whatever you did when you balance this equation become exponents in that equation. So let's look at a real example here. I'm going to do the first example. I'm going to give you some time to struggle on the second example. So here are my products. So they go on top, oxygen's on top, and it is to the 3rd power, or cubed, if you will. And then does anyone in either room know the name of O3, its common name? No, not trioxide. That's a good guess, though. No, no, peroxide, no. Anyone in the other room?
Ozone.
Ooh, who's the smarty? Wahaj? Oh, that's cheating. Wahaj took AP last year. So yeah, O3 is the formula for ozone, the gas that blocks infrared light and stuff from entering our area, our atmosphere as well. So this is the ratio: oxygen to the 3rd power over ozone to the 2nd power. Now, I'm going to pause my video while you guys try to work out the other one. Please keep in mind, when the plus sign is here, it becomes what in the expression? Yeah, multiplication. Okay, pause while you guys are around. All right, Caroline. So here's the pen of awesomeness. What's going to go on top?
2HF.
Oh, the 2 becomes a... I know I'm right. I teach this for a while now. So the HF goes on top, and it gets squared. Nice work. And then on the bottom?
H2.
Yep, H2 times F2. Nice job, Caroline. And we just put them in brackets. That's not wrong. We put them in brackets. Brackets represents that it's the molarity of the substance. Sometimes people put parentheses. That typically in chemists' mind mean pressure. I know that's really weirdly specific. Any questions for Caroline? Yeah, her handwriting's pretty good. I'm kind of jealous. Although these are some of my best oxygens ever. Yeah, great. She multiplied, not added. Multiplied them together. Now the next step, which we're going to see on the next page, but I'm not going to go there quite yet, is it might give you values. So let's say that I give you some values. And I say, hey, HF has a molarity of 5, so that's going to be squared. And hydrogen is a molarity of 1. And fluorine is a molarity of, I don't know, 2. I'm just making numbers up. Normally I would give you data. And so then you could solve for K. What is 5 squared? What is 1 times 2? What is 25 divided by 2? So K with this fake values would be like 12 and a half. All right? So in the next statement, in the next page, we're going to make one room. We'll call this room 1. And the other room, room 2. You got that, people in the other room? Okay. Your room 2. Your experiment 2. So the expression is KSO3 squared divided by O2 times SO2. Now here's my warning. Here's my warning. And that's supposed to be squared. I already screwed up. Nice work. These values are on the bottom, right? In your calculator, put parentheses around them so that your calculator knows this divided by all that janks. Not just the top divided by some of it, right? And don't forget the squares. So room 1 here, you're going to plug this data in. Where should this value go? The 1.25. Where the oxygen is, right? Where should the 3.5 go? On top. Now don't forget, 3.5 is going to be squared. 1.5 is going to be squared. Group 2 in the other room, you're doing experiment 2. I'm going to give you about 3 or 4 minutes. Then I expect you to send a member to this room and work it out on the board. Not Wahaj. I don't want to see him. All right. So we have K for experiment 1, brought to you by Caroline, and K for experiment 2, brought to you by Felicia. I'm making up some names today. Here you go, Caroline. There you go. All right, hand it to her. What's that? So I have 2 great questions here. First of all, a question from some random person in the room was, am I going to count sig figs? I would like to see you round it somewhat appropriately. If you did this, these are perfect sig figs for both answers. I could see someone named, I don't know, Billy, going 4.3700155789. Okay, it's evidently somebody named Sean. That is just way too many sig figs, right? And that is definitely when you get the attention of your teacher, and they go, what are you doing? -1, right? But if you are rounding pretty appropriately, most of the time we don't even notice. That's a little, secret there. Why aren't these answers the same? They rounded differently. The numbers are slightly different. But what does K stand for? Constant. Good job, Felicia and Caroline. Yeah, these answers came out the same even though the numbers are different. That's just like when I say, hey, what is 4/2 the same as? There's a lot of answers to that question, aren't there, though? 4/2 is also the same as 16/8. As 100/50, isn't it? There's a billion different answers to that question. Usually, though, we just reduce it down to 2. So this ratio and this ratio are actually the same ratio. They're both 4.3-ish over 1. And that's what was interesting about equilibrium is they come to the same constant. You guys just going to chill there?
Can we actually?
All right, class vote. Can they stay here? That was a no.
Bye, Felicia.
All right. Wow. That was a little harsh. Homogeneous and heterogeneous. Most of us know that homogeneous means all the same. Heterogeneous means slightly different in some way, right? So with these two terms, we are talking about the states of matter. We have solid, solid, gas. Solid, solid, gas. Would that be heterogeneous or homogeneous? Heterogeneous. We have solids and gases mixed together. Remember earlier when he said in order to find a date to the prom, you need to collide with them and knock the books out of their hands? These solids are the kids sitting on the floor, right? The kids sitting on the floor before school, they're not moving around. You might trip on one, fall on, and then knock the books out, and maybe that works. But they are not actively seeking anyone out. They, solids, get represented as the number 1 in our expression. Also, liquids get represented by the number 1. And the reason that solids and liquids don't get represented in expressions is they're so slow. How fast does a rock move when it's just sitting on the ground not moving? Really close to 0, right? It's vibrating a little bit, but not much. Air moves at 240 meters per second. Air can run the mile in about 5 seconds. Yeah, that's the new pacer record, right? So it can set, and so since gases are so much faster, they're the only important factor in a lot of these. We also include any aqueous ions for things we'll discuss later. But so initially we'd probably want to set this up as products, KO times CO divided by KO. But KO and KO are both solids, so we're going to some odd time warpy thing going on over here. Because we can hear your bell in the other room, but it's a delay, so it's really weird. So these two solids get replaced with the number 1, and therefore K equals 1 times CO2 divided by 1, which is commonly just written as CO2. All right? Because those two objects are solids and not moving. Yes, ma'am. Caroline.
Why did you put the Keiko?
Yeah. So the question is, why did we put the CaCO3 on the bottom, the calcium carbonate? It's a reactant, so the reactants always go on the bottom. The products, the things on the right, always go on the top. I often think that this is another example of the right-handed people trying to show their dominance over the left-handed people. We put the left on the right on the top, and we're keeping the lefties down. And I don't approve of that as a recovering left-handed person. Yes, usually though the reactions are put on the left because that's like what you started with. Like I have this rock, and then slowly this rock breaks apart and makes those things on the right side. So I started off with this thing, let's call that the reactant. The most common example people see in their regular boring lives is this compound here, which is called carbonic acid or carbonated water. It's found in sodas. And it breaks down, makes carbon dioxide, right? And it sounds like this. Right? You've heard that noise before? Right. Yeah. That's a pretend soda bottle. I'm not passing sodas out in here. Don't get excited. You can actually reverse that reaction. You can recarbonate your water. If you like have a flat soda and you want to make it carbonated again, you just need to put the carbon dioxide back in, and you can push it in reverse. That reaction's dependent on the amount of carbon dioxide. People having fun in the hall. That's a liquid. This is a gas. The gas floats away. If you put the gas back in, you can make it carbonated again, which is what they do at most stores. They have a CO2 line that feeds into the solution to make it carbonated. You could buy dry ice. You have a machine that carbonates? Cool. I'm kind of jealous. She has a machine that makes her own soda. You could just buy dry ice, though. You throw dry ice in your punch. Next time you throw in a party, Louis. You throw a piece of dry ice in the punch, you actually have carbonated punch. Because the carbon dioxide, as it bubbles into the gas phase, will carbonate your punch, and you'll be drinking carbonated punch. Yeah. That's how we roll at the chemist parties I throw. So this one would be 1 squared over H2 squared times O2. Why 1? That's a liquid. We replace solids and liquids with 1. Do I really need to write 1 squared? No, because 1 squared is 1, right? But I'm just trying to, hit all of those things and be super thorough right now. Oh, I forgot about this. Oh, that's really upside down now. So let's see how they look. It's been a while. Been a long time since we looked at these. No, that's the wrong thing. There we go. At least they're not upside down. So we have the regular temperature, which is purple. We have the one that's in the hot. Definitely. Can you guys tell that's blue next door? Yeah. And then I have the one that's in the cold. Ooh, thank you for the ooh. Makes me feel like people are paying attention. Both of you. That was all caused because we're changing the temperature. We're shifting those reactants around. All right. Creepy guy. All right, I think we're almost done. We're now at the time when the bell rings. So here we just have some simple math. We set up the expression H2 squared times O2 over the H2O squared. And as you can tell from the question, we have values. What do you think we could do with these values? Plug them in. And we have 1, 2, 3, 4 values, and they're giving us 3 of them. So we have plug in all we have and do the algebra from the missing thing. What's weird about this particular unit is you create the equation, hopefully correctly, and then plug the numbers into the equation and do the algebra, hopefully. So we have a K of 2.4 times 10 to the minus third equals 0.11 squared and 0.019 squared, but we don't know oxygen, so I'm going to be boring and throw an X in there for oxygen, and then I pull out my calculator of fun and I solve for X, and I get an answer that I can't remember, but I have a calculator, so I'll just redo it. So after doing the algebra, I got 0.080 for my X value. But I am algebra insecure, like so many kids on the planet. I'm going to take that value and plug it back into here and see if these things equal that. Right? Shouldn't that work? So I'm just going to take my 0.019 squared times the 0.08 that I just got, divided by 0.11 squared, and see, yeah, I got a really close answer to that. Why am I not going to get a perfect answer, perfectly equal? Do you think this is the actual value in my calculator? That's a rounded value. So it's going to be slightly off when I go to test to make sure I did my math right. Super common for people to make tiny mistakes. Who's made a tiny mistake in this room? Right? And I'm not talking about your hair, but yeah, we've all made mistakes. Especially in a calculator, it's so easy to accidentally cube something instead of square it or whatevs. All right, K is equal to N2O4. Does anyone know the name of N2O4, the common name? Has anyone ever inhaled N2O4? It's called laughing gas. Yeah, N2O4 is laughing gas. Some of the people over here look like they're inhaling it right now. It's not true. It knocks me out, so I don't ever remember what it's like. I had to have it once when I had my wisdom teeth yanked out. Yep. And I don't remember from the moment they say count backwards from 10, and I was like 10, 9. And when I woke up, I said 3, 2, 1. I mean, I woke up like 2 hours later, and I finished the countdown. And evidently that's pretty common because your consciousness like slips away and gets like stored over on the side for a little bit. You got to 7?
I got like 10, 9, 8. My 8
Man.
I got 7.
Oh, wow. She fell asleep crying, went through the whole surgery, woke up crying. Is there? He's doing. X squared would equal 0.45 over 1 times 10 to the 4th. Algebra occurs, and I take a square root. If I want to solve for x, don't I need to take a square root? And I think we can all do that in our head. The answer is 0.0067. Maybe that's wrong. Maybe I should grab a calculator. No, that's right. This is the 3rd time I've done this today, so I've got some of the answers memorized. Yes, Caroline. Dun, dun, dun. You know, if you want to be right, you could be right. Yeah, this should be, the answer should be molarity there, shouldn't it? There should be an M on both of those. She was just pointing out that I left my units off. Now, I do want to make one weird unit statement. For the very first time in the entire history of this class, you're not going to write units down on K. K has no units. K is weird, because here, in the first problem, it would be molarity squared times molarity divided by molarity squared. And molarity squared divided by molarity squared would cancel out, wouldn't it? And then you'd only have this molarity left, so K would have 1 molarity value. But in the other one, it'd be molarity over molarity squared, which would be 1 over molarity. Because K's have really random, weird units that just depend on the expression, people decided to punt the units a long time ago. So they just say what the equilibrium constant is, and they give it to you. Okay, we are going to shift quite literally, because that's the next section, is about shifting, to Le Chatelier's principle, which in Southern Virginia is pronounced Le Chatelier's. Le Chatelier is a French scientist who measures shifting. And the whole reason that I did this thing here, that's just a black box now. The whole reason I did the test tube thing was to be an example of shifting. How did I cause the color of that and the shifting in that reaction to occur? Heat or ice. I put it in hot water, I put it in ice, I changed the temperature. We can also change the concentration, the volume, or the pressure. And this is what Le Chatelier was studying, is how to shift reactions. How to make reactions move from one side to the other side. In these scenarios, and when you guys do homework worksheet 1 tonight, shocker, worksheet 1's your homework. Have you picked up the pattern yet? That at the end of the notes, you then do worksheet 1. And then what do you do after worksheet 1 the next day? Worksheet 2. This guy can't get it. He's not very good at patterns. After tonight's homework, shocker, you're going to see some questions like this in worksheet 1. This reaction is supposedly at equilibrium. Okay? And then a guy comes along. Let's call him Sean. And Sean messes with the reaction. I like to imagine every reaction like it's a seesaw. And that there's pieces on both sides of the seesaw, and that these pieces are currently in balance. And then along comes Sean, and he adds an object to one side. Now, why is he adding? So increase the concentration of CO2. CO2 is on the left side. So I imagine it on the left side. This side's too heavy now, isn't it? Would it be in balance? No. Where would you need to add an object to bring it back to balance? You need to add it to the right side. You need to add something to the right to bring it back into balance. That is a good visualization, but not even remotely close to reality. So what really happens is that when Sean adds extra carbon dioxide into here, these pieces can collide. And if they collide more, they're going to react faster. And as they react faster, the reaction's going to go that direction, a little bit faster. So you're going to see a shift to the right. You're going to see these pieces being produced and these pieces seeing products produced and reactants lost. Wouldn't be the notes if he didn't hiccup, would it, guys? So that's a constant for me. Sounds like a pterodactyl got attacked. Swallowed. Now Sean comes back and Sean adds oxygen. Oxygen's on this side, so he's added some oxygen. Again, this side, the product side is now too heavy. How would you balance out his new chicanery? You would add something to the left side to balance it out. Again, I like the teeter-totter idea, the seesaw, but if you think of oxygen as being added, would you have more or less collisions if there was extra oxygen over here? There's dead silence in this room. What about the other room? Do you guys think we'd have more collisions on the product side or less collisions now that there's more oxygen? More. We'd have more, and then this reaction would shift left because there's so much more on the right side to collide, it would shift left. Shifting means it would react and move left. Removing is even easier. Let's say that someone named Ryan removed all of the carbon dioxide. This side of the reaction stops, because if you don't have something, it can't react. Does this side of the reaction stop without carbon dioxide? No, keeps running. So this side still goes that way, and it would shift left and replace the carbon dioxide. Removing the carbon monoxide, it's going to shift right to replace what was stolen. All right, erase, erase, erase. Let's get rid of the seesaw. There aren't enough good seesaws anymore. Oh, weak. Got those like little bubbles underneath them so you can't get hurt. Psh. All right. Shifting to the next question. Volume and pressure. I want to remind you here that volume and pressure are inverses of each other. Does anybody remember the name of this equation that I just wrote down? Starts with a B. Boyles. Yeah, Boyles Law. That's Boyles Law. And as the pressure, as the volume decreases, the pressure increases. They are inverses of each other. I am much better at imagining volume than pressure. What did I just say? Pressure? Than pressure. So when it says in B, increase the pressure, I usually translate that in my head to say decrease the volume. Because I'm better at imagining things getting bigger or smaller than I am more pressure and less pressure. So I usually just flip those around so I can imagine it better. On the left side, we have 1 particle and 3 particles for a total of 4 particles. Do you agree? But on the right side, we only have 2 particles. If you made the hallways smaller, who would collide more often? A group of 4 or a group of 2? The group of 4. The large side is impacted more by these changes than the small side. So if we decided to make the volume of the hallways smaller, the 4 would be impacted way more than the 2. And we actually did this about 10 years ago. We made the hallways smaller at Potomac Falls. Does that sound insane? Yeah. Have you ever been to the freshman hallway, though? There's these weird-looking lockers down there, aren't there? That aren't recessed in the wall like here on the junior hallway. And that was because we started to grow in size. We needed more lockers. And we put a hallway full of lockers. That hallway is the skinniest hallway in the school because of those lockers. And if you tried to walk at the same width that people walk down here, like 12 people across, you would definitely collide into each other. Decrease the volume. These guys start to react. The four react to a whole lot, and it shifts right. Shifts right because they can't take all that increased collision. B is also the same as decreasing the volume. An increase in pressure is more collisions, which is the same as decreasing the volume. What would happen if you increased the volume? Which way would it shift? It would go left. Yep. It would go the opposite. And again, if you were walking down the hall with 3 of your friends, ergo there are 4 of you, versus you're walking down the hallway with 1 of your friends, ergo there's 2 of you, you notice the hallway shifts more when there's 4 people because you can spread out, but it's hard to contract. When there's just 2 of you, you're like, it doesn't matter that the hallway's skinny. It's just 2 of us. So the 4 is impacted a great deal more. You have to count up how many moles are being impacted. And lastly, this is generally the easiest part, is changes in temperature. Exo means energy's going out. It is a product. Endo means energy is going in. It is a reactant. So I will often write the word heat directly into the equation. So if it's endothermic, where should I write heat? As a reactant or a product? Reactant. Yeah, it's taking in heat. It's endo. So I'm going to put it as the reactant as if it's absorbing in heat. Conversely, if it had said it was exothermic, I would have written it on the other side. So boiling water is endothermic. You put heat in, and then the particles you make are carrying that heat afterwards. So if we increase the temperature, that's like putting in more heat, isn't it? So this reaction would shift to the right by adding more heat. Decrease the temperature, it's like you're removing this heat, and then it would shift to the left. To the left, to the right, to the right. All right. Wait. A request for waiting on this side. Man, I really hope that this video works. This will be attempt number 3. I've been recording all of this nonsense the whole time. Hopefully it works. Right. That's the deep sigh of fear. All right, last question and then we're done. Big stretch. Exothermic, making heat. Heat's a product. Increase the temperature. This one would shift left. It'd be extra heat. Heat plus SO3 would push you left. Add SO2. That's on this side. That would shift you right. Volume decreased. Is it going to go to the bigger side or the smaller side if the volume decreases? Smaller side. So we got to add them up though. This is 3 moles of gas. This is 2 moles of gas. So it's going to go to the right, which happens to be the small side. Oxygen's removed. This side of the reaction stops without oxygen, but it could still go towards that. When you remove something, the reaction will often replace what you've removed. E, pressure is increased. That's the same as a volume decrease, so it would shift to the right. Decrease the temperature, that's removing the heat. It would shift also to the right. Next class, your teacher, whoever that person may or may not be, is going to talk to you about the Haber process, which is the most important reaction to humanity in quite a long time. 2 more. What are the 2 more? Oh my God, how have I gotten this far in the day and no one's pointed out that there are 2 more? A, B, C, D, E, F. What does G say?
Add argon to the reaction.
Oh, add argon. That's where all my good jokes went. Argon is a noble gas. Does it react with elements? No. No triangle. Triangle stands for change. No change. If you add argon in there, they're going to be like, hey, what's up, argon? We're not shifting, though. You have no impact on us. And then H? add a catalyst. Okay. I don't know why for a second I thought you said add cattle. I was like, I don't know how adding cattle would change this reaction. Add a catalyst. So adding a catalyst speeds up a reaction and gets you to equilibrium sooner. Now let me address this perspective though. This reaction is this reaction is already at equilibrium. If you add an catalyst after you're at equilibrium, would it change? No. This is the equivalent of, and it's going to be goofy, but just pretend that there's a girl named Megan. She's just recently gotten married, and then she joins Tinder. That's a little bit late to add the catalyst to finding your potential husband or wife, right? After you've already found him. It's a little late. You don't add the catalyst after you've reached equilibrium, you add it before. Okay? Now, I'm not endorsing Tinder by any means. I just want to make that clear. Meet people however you want to meet people. Next class, you're going to learn about the Haber process. The Haber process is responsible for the lives of, what's 2/3 of 7? 2/3 of 7 billion people on the planet depend on the Haber process, including Americans. The Haber process produces fertilizer. Fertilizer makes food. Before the Haber process was perfected, our population didn't grow too much. And you will learn way more about that and possibly other disgusting things. Here's where I hope the video takes.